Space is vast. It's filled with mysteries that boggle the mind and stretch the limits of our understanding. From the smallest particles to the largest galaxies, the universe is a treasure trove of secrets waiting to be uncovered. One of the most fascinating and enigmatic of these secrets is the Gravastar. This theoretical object challenges our conventional understanding of the cosmos. We know about black holes. They are regions of space-time where gravity is so intense that nothing, not even light, can escape their grasp. These cosmic giants are formed when massive stars collapse under their own gravity. The gravitational pull of a black hole is so strong that it warps the fabric of space-time itself, bending light and trapping anything that comes too close. But what if I told you there's another possibility? A possibility that defies our current understanding and opens up a whole new realm of cosmic phenomena. What if some massive stars, instead of collapsing into black holes, transform into something even more mysterious and exotic? What if they become gravastars? These hypothetical objects are unlike anything we've ever seen or imagined. Gravastars, short for gravitational vacuum stars, are theoretical objects that could form when a collapsing star's core is replaced by a region of dark energy. This creates a stable yet incredibly strange object. They challenge our understanding of gravity and the fundamental laws of physics. Gravastars could potentially offer insights into the nature of dark energy and the true structure of spacetime. They make us question everything we know about the universe. Could these objects really exist? And if so, what would they mean for our understanding of the cosmos? Join me as we embark on a journey to explore the mind-boggling concept of gravastars. Together, we'll delve into the theories and ideas that make these objects so fascinating. Let's delve into their formation, their unique properties, and the cosmic events that could lead to their creation. And let's explore their potential impact on our understanding of the universe. Gravastars could revolutionize our knowledge of the cosmos and open up new avenues of scientific discovery. Stars are born from clouds of gas and dust. These clouds are huge. They are called nebulae. Nebulae are the stellar nurseries of the universe, where the magic of star formation begins. These vast regions of space are filled with the raw materials needed to create stars. They are often illuminated by the light of nearby stars, creating stunning and colorful displays that can be seen through telescopes. Gravity pulls the gas and dust together. The cloud collapses. This process is known as gravitational collapse. As the particles within the nebula come closer together, their gravitational attraction increases, causing the collapse to accelerate. Over time, the cloud fragments into smaller clumps, each of which can potentially form a new star. As it collapses, it heats up. The temperature in the core of the collapsing cloud rises dramatically. This heating is due to the conversion of gravitational energy into thermal energy. As the core temperature increases, the pressure within the cloud also rises, counteracting the force of gravity and slowing the collapse. The core gets really hot. Eventually, nuclear fusion begins. Nuclear fusion is the process by which lighter atomic nuclei combine to form a heavier nucleus, releasing a tremendous amount of energy in the process. In the case of stars, hydrogen nuclei fuse to form helium, providing the energy that makes stars shine. Hydrogen atoms fuse to form helium. This fusion process releases energy in the form of light and heat, which radiates outward from the core. The energy produced by nuclear fusion creates an outward pressure that balances the inward pull of gravity, allowing the star to achieve a stable state. This releases a tremendous amount of energy. A star is born. The newly formed star begins its life on the main sequence, where it will spend the majority of its existence. During this time, it will continue to fuse hydrogen into helium in its core, producing the energy that sustains it. Some stars are much more massive than our sun. These stars burn bright, they live fast, and they die young. Their deaths are spectacular. Massive stars have much shorter lifespans compared to smaller stars like our sun. They exhaust their nuclear fuel quickly, leading to dramatic and violent ends. They leave behind some of the most enigmatic objects in the universe. When a massive star dies, it can explode in a supernova, leaving behind remnants such as neutron stars or black holes. These remnants are incredibly dense and have extreme gravitational fields, making them some of the most fascinating objects in the cosmos. Massive stars live fast and die hard. They burn through their fuel quickly. When the fuel runs out, the outward pressure from nuclear fusion stops. Gravity takes over. The star's core collapses in on itself. This collapse is violent. it triggers a supernova explosion. The outer layers of the star are blasted into space. What's left behind depends on the mass of the core. If the core is massive enough, it collapses into a black hole. But what if there's another possibility? Some scientists believe that extremely massive cores don't become black holes. Instead of collapsing into a singularity, these cores might undergo a different transformation. This idea challenges our traditional understanding of stellar evolution and the fate of massive stars. Instead, they might become gravastars. A gravastar, short for gravitational vacuum star, is a theoretical object that could form when a star's core collapses, but doesn't turn into a black hole. This concept was proposed as an alternative to black holes, suggesting a different end state for massive stars. The idea is that the collapsing core encounters a quantum physics effect. Quantum mechanics, which governs the behavior of particles at the smallest scales, introduces phenomena that can alter the fate of collapsing stars. These effects are not present in classical physics and can lead to surprising outcomes. This effect halts the collapse before a black hole can form. Imagine a star collapsing. As the core contracts under gravity, it reaches a point where quantum effects become significant. These effects can create a repulsive force that counteracts the gravitational pull, preventing the core from collapsing further. It's like a falling domino. When you set up a line of dominoes and push the first one, they all fall in sequence. But imagine if, just before the last domino falls, an invisible hand stops it. This is similar to how quantum effects can halt the collapse of a star's core, but just before it reaches the ground, something stops it. This sudden halt is due to the quantum effects that create a repulsive force, acting like a cushion that prevents the core from collapsing into a black hole. That's the idea behind gravastars. They are hypothetical objects where the core's collapse is stopped by quantum effects, resulting in a stable, dense object that doesn't become a black hole. This concept provides an intriguing alternative to our understanding of stellar remnants. A quantum bump prevents the complete collapse. This bump is a manifestation of quantum mechanical principles that introduce a repulsive force at extremely small scales. It's a fascinating interplay between gravity and quantum mechanics. This bump is a theoretical concept called the quantum vacuum polarization. It's a complicated idea. Quantum vacuum polarization refers to the process where a vacuum, which we usually think of as empty space, is actually filled with virtual particles that pop in and out of existence. But it essentially means that empty space isn't really empty. Even in a vacuum, there are fluctuations that create pairs of particles and antiparticles. These virtual particles can have real effects on their surroundings. It's full of virtual particles popping in and out of existence. These particles are constantly being created and annihilated, contributing to the overall energy and dynamics of the vacuum. These particles can exert pressure. The presence of virtual particles can create a pressure that opposes the gravitational collapse of a star's core, acting as a counterforce to gravity. This pressure could be enough to stop the collapse of a massive star. If the repulsive force generated by quantum effects is strong enough, it can prevent the core from becoming a black hole, leading to the formation of a gravastar instead. This theoretical concept opens up new possibilities for understanding the ultimate fate of massive stars. Section 5. Anatomy of a gravastar. Peering into the void. So what does a gravastar look like? Imagine a bubble. The surface of the bubble is a thin shell of incredibly dense matter. This shell is held up by the quantum vacuum pressure. Inside the shell, there's something even stranger. There's a region of spacetime where time and space are distorted. This region is called a de Sitter space. It's a theoretical concept, but it's a key part of the gravastar model. Section 6. Gravastars versus black holes. A Tale of Two Singularities. Gravastars and black holes are both extreme objects. They form from the collapse of massive stars. But they are fundamentally different. Black holes have a point of infinite density at their center. This is called a singularity. Gravastars, on the other hand, don't have a singularity. The quantum vacuum pressure prevents the collapse to a point. This difference has profound implications. Black holes are regions of spacetime from which nothing can escape. Gravastars, however, might allow some information to escape. Section 7. Observational evidence. The search for gravastars. Gravastars are still theoretical. We haven't observed one directly, but some observations hint at their existence. For example, some distant objects emit bursts of gamma rays. These bursts are incredibly energetic. They could be the result of gravastars forming or colliding. Scientists are actively searching for more evidence of gravastars. They are using telescopes to study distant objects. They are also developing new techniques to detect gravitational waves. These waves could be produced by gravastars. Section 8. Theoretical Implications. Rethinking the Universe. The existence of gravastars would have profound implications for our understanding of the universe. It would mean that our understanding of gravity is incomplete. It would also have implications for our understanding of the early universe. Some scientists believe that the entire universe might have formed inside a giant gravastar. This is a radical idea, but it's a testament to the potential impact of gravastars on our cosmological models. Section 9. Conclusion: the everlasting allure of the unknown. Gravastars remain a mystery. They are a product of our imagination. They are born from our curiosity about the universe. Whether they exist or not is still unknown. But the search for gravastars is a testament to the power of human curiosity. It's a reminder that the universe is full of surprises, and that our journey to understand the cosmos is far from over. The universe is vast, it's full of mysteries, and the quest to unravel them continues.